So this video is going to be the last in my series on applied physics. So it's going to look at the second law of thermodynamics and how it can be used to explain how we can extract work from hot objects and how we can create heat pumps and how we can create refrigerators. So to start off with the Carnot engine. So essentially this is an engine that's trying to get work out of a hot source here. So what we have is an infinite source of high temperature here and an infinite source at a colder temperature here. And the reason they're infinite source is losing energy doesn't change the temperature of this. So this will stay at TH the whole time, this will stay at TC the whole time. And what we're doing is we're getting work out of it. The first thing we want to do is apply conservation of energy and generate an expression for the work done. So the total energy going in must be the total energy coming out, conservation of energy. So the energy going in is the heat removed from the hot source, which is QH, and that must be equal to the work done plus the energy delivered to the cold source. And by rearranging that, we can get an expression for our work done in terms of the temperature difference. So the amount of work done by our engine is actually nothing to do with the engine at all. It's just to do with the difference in the energy delivered from the hot source and the energy delivered to the cold source. So that's that one. So if we wanted to calculate the efficiency of our system, the useful energy is the work, because that's what we want it for, and the amount of energy delivered would be the energy from the hot source. So that's your QH. Let's substitute in our expression here. Minus QC. And that gives you this expression here. So you can get the maximum theoretical efficiency of your engine is calculated using this here. So what will be really useful is actually to look at this in terms of the temperature, because that's something we can easily measure. Measuring the energy given off is quite tricky. And because the energy delivered is directly proportional to the temperature, because hotter objects give off fast heat at a faster rate, and in a Kelvin scale they're directly proportional to each other, so we can actually get this expression for efficiency in terms of the temperature of the objects. So what we can see is it's impossible to achieve an efficiency of 100% or 1, because it's impossible to get to absolute zero here. So that's what the second law of thermodynamics is kind of telling you. It's impossible to transfer thermal energy usefully into other forms of energy, and this equation is what allows you to explain why. So before we go on to look at reverse heat engines, or looking at essentially how they can be used for refrigerators and heat pumps, we need to have this thing called the coefficient of performance. So it's a measure of the amount of heat you deliver in terms of a heat engine, or the amount of energy you remove in terms of a refrigerator, and you divide it by the work in, and that tells you essentially how good it is at its function. So here is a setup of a reverse heat engine, and we could be using this as either a refrigerator or as a heat source. So if we connect our house here in the hot position, what we'd be doing is putting work in and it's delivering heat to your house, which is very nice. It keeps you nice and warm. Or what you could do is connect this side to a refrigerator or something you want to keep cold, and by putting work in and pumping heat into a hot reservoir, you're removing heat from here. Again, very useful. Okay, so what we want to do is think about the efficiency. So for a heat pump, which is when you're trying to get heat out of it, essentially you're using it as a heater. So the useful energy out in a heat pump would be the QH, and it's divided by the work done. And here is your work done, so that's going to be, in this case, QH minus QC. And this is known as the coefficient of performance of the heat pump. So essentially it's a measure of how good it is at pumping heat. We want to do this for a refrigerator. Your efficiency would be the useful heat transfer, which would be QC, because you're trying to remove heat, again divided by work, which would give you QC over QH minus QC, which is also known as the coefficient of performance of refrigeration. So by changing the subscript, you essentially change what it is. And just like before, we could have easily swapped in temperatures instead. So you can see that essentially these expressions are a measure of essentially how good your heat engine or your refrigerator is at delivering what's useful. And these numbers here are often quoted for them, so you can instantly get an idea of how good your heat engine or your refrigerator is. So in terms of this, so what's the point of having a heat engine? Surely we can just put some electricity into a heater or something and you can get heat. Isn't that enough? Well, actually, these are better because you're still putting work in just the same as you would for an electric heater, but because you're drawing energy from other sources as well, you actually get more heat energy delivered to whatever you want heat for the same amount of work. So that's an advantage they have over just conventional, like an electric heater, for instance. There are problems with them though, in that you can never reach 100% efficiency, which is not great. And so one of the barriers is the second law of thermodynamics, which is kind of a big barrier and is therefore quite annoying because it's not possible to transfer all heat energy into other forms, making 100% efficiency not possible. And the other thing is, because you've got all these expressions have a temperature of your cold in them, because it's absolute zero is not achievable, and actually it's usually room temperature, because with a refrigerator we're pumping out of like a fridge, or you're like with a heat engine you're pumping to like surroundings. There's always going to be issues with that, and that's always going to lower the efficiency of your overall thing. And with your heat engine where you're getting work out, that's going to be a source of inefficiency as well. So that's a lot of stuff. Let's see this put into practice with some questions. Okay, so first question, what is the coefficient of performance of a heat pump? So it's the energy delivered to the area being heated, because that's what you're trying to do with it. And then you divide that by the work you're putting into the system. That's what your coefficient of performance is. Be very careful about being vague with these kind of questions. Don't just say something like heat input or something like that. You need to explain what you're using it for. So you're using it to deliver heat to a hot source. So you're delivering energy to somewhere that you're trying to heat, and it's divided by the work input. Okay, so we've got some diagrams here. The box there shows a diagram, combined heat and power scheme. The scheme provides electrical energy from an engine-driven generator, and it's heating buildings essentially that are near to the generator. So the electric energy is used to drive the heat pump, as shown in this diagram here, and Q2 is used to heat buildings. So this is essentially a way of utilising power stations. You might assume that the engine runs at its maximum theoretical efficiency. An electrical generator is 100% efficient. The output power of the engine-driven generator is is 80 kilowatts. So we're using some fuel with this amount. Calculate the flow rate of it. Okay, so let's see where we're going to go with this. Okay, so it says it's running at maximum theoretical efficiency, so we're going to need to calculate what that is first of all, because remember it's not going to be 100%. So to get our efficiency, you're going to use our formula like this to get work out of it. So that's going to be 1600 minus 290 divided by 1600, which is 0.82. So the ratio of power in to power out essentially is going to be 0.82. So your power in is going to be power out by 0.82, which is around about 98. I'm not rounding in the calculations, but that's going to be in, which is going to be equal to the mass flow rate times the calorific value. So that means your mass flow rate is going to be your 98 divided by the calorific value, which is what? 49 times 10 to the 6. Remember, this was in kilowatts, so that should be times 10 to the 3. And then if you put all those in, you get essentially 2.0 times 10 to the minus 3. Should have given myself more space. And then remembering your unit, it's a mass flow rate, so it's going to be in kilograms per second. Okay, cool. So that's that question there. So I used a bit more space than I was planning. Never mind. The heat pump has a coefficient of performance of 2.6. The power supplied by electric generator to the heat pump is 16 kilowatts. Calculate the total rate at which energy is available for heating from both the engine and the heat pump. So first of all, your coefficient of performance is the heat energy delivered divided by the work done, and therefore you can calculate this. So it'd be 2.6 times by 16 times 10 to the 3 is 41.6 kilowatts. But remember, we also had some heat energy supplied from the initial stage, so we supplied 98 into it and got 80 useful kilowatts of energy, so that gives you 18 kilowatts from the first stage as well. So then when you add those two together, that would give you the total amount of heat available, which would come, when you add them together, would give you 60 kilowatts of energy supplied. So with these questions, remember, because it's got two stages, it's got the final heat pump delivering this much, and then the initial stage, you're getting this much energy out of it, so then you're adding them together, so you can actually increase the amount you're getting, which is always nice. It's always good to get something for nothing. So then last part of this question, before I move on to the next question, the conversion of electrical to heat is nearly 100% efficient. Explain why the designer has proposed installing a heat pump rather than electrical energy. So you get you get more heat energy for the same work. Because you're essentially adding to the work to the energy from the hot source. Okay, so then is asking you, we're moving on to question 2 here, what is a reversed heat engine? So essentially, a heat engine, you're taking heat energy and getting work out. Here you're putting work to transfer energy from a cold source to a hot source. That's the idea. So whether the idea of it is to take energy away in a refrigerator or give it to somewhere in a hot to make it warmer, it's still transferring energy from a cold source to a hot source by putting work in. So there's input work, so it's going from cold to hot. So then explain why the coefficient of performance of a reversed heat engine when operating as a heat pump is always greater than the coefficient of performance of the same reversed heat engine when operating as a refrigerator. So first thing, when we're dealing with this, so your Q in is going to be your work done plus your Q out here, if we have this expression. So if we think for a heat pump, it's the Q in that's important, and then for the refrigerator, it's the Q out that's important. So what we can determine from here is that actually Q in is always greater than Q out because it's essentially got the work added to it. So coefficient of performance of a heat pump is going to be Q in over W. Coefficient of performance of a refrigerator is Q out over the work. And if Q in is greater than Q out, that means the coefficient of performance of the heat pump must always be greater than the coefficient of performance of a refrigerator. And you can see it from that sort of logic there. Okay, let's move on to the next question. So the coefficient of performance of a refrigerator is given by this expression here. Explain what Q in and Q out are. So essentially, the Q, this is your refrigerator here. You're putting work in, and then you've got your hot space. Let's make it red. So Q out is going to be the energy removed from your cold source, and your Q in is going to be the energy given to your hot space here. So it's essentially that's what is going on, and that's what they represent. So a refrigerator is designed to make ice at minus 10 degrees from the water, initially at room temperature. The energy needed to melt a kilogram of ice at minus 10 degrees is 420 kilojoules, and it has a coefficient of performance of 4.5. Calculate the power input to the refrigerator if it is required to make 5.5 kilograms of ice every hour. Okay, so let's first calculate the energy removed from the ice in, let's say, in an hour, just to keep it in the same units as in the question. So this is your mass of ice, and this is your energy per kilogram. So that's going to be 2310 kilojoules. Now, remember your coefficient of performance is your Q out, and you're going to divide that by the amount of work you've put in. Which means that the work is going to be divided by coefficient of performance is 513 kilojoules, so that's the amount of work done in 1 hour. So let's just scroll over here. So we want to calculate the amount of power put in, so this is the amount of work we put in, so we need to divide it by the time. 513 divided by 3600 to convert it into joules, and that comes out as 142 watts of power. So what we've done there is first of all calculating the amount of energy removed from the ice in order to cause that temperature change. We've used the coefficient of performance to work out how much work we'd have to put in to do that, and then once we've got that work, divide by the time to convert it into a power. So I want to calculate the energy is the rate at which energy is delivered to the surroundings. So your energy delivered to your surroundings is going to be the energy removed plus the work done. That's going to be 232,310 plus 513. Using the unrounded versions, you get 2820 kilojoules. So then we've got the work done. We need to convert that to a power. And that's going to be 28200 times 10 to the 3 divided by 3600 to get power, and that gives you 784 watts of power delivered to your surroundings in form of heat.